Hanoch SENDEROWITZ, our friend from the Ilan University, who is the absolute champion of diversity, not necessarily molecular diversity, but application domain diversity. He has contributed to everything from forensics and police work to agricultural application to material science to complex biological system and so on and so forth. So today he is materials informatics once again, and it's green. So Hanoch, please.
Thank you very much. And it's really an absolute pleasure to be here again. Thank you, Sasha, for inviting me. So that's the official talk of my lecture, Material Information for Green Energy Harvesting and Storage. This is the alternative title, being the last speaker of the conference. And this is the presentation outline. So I don't know if you know this text. This is taken from the Victorian time, and this lists what a bride should wear on her wedding day. So something old, something new, something borrowed, something blue, and a sixpence in her shoe. So for something old, some published result. For something new, some unpublished result. Something borrowed. So we are going to borrow quite a lot from Chemoinformatics, into material informatics. Something blue, I couldn't find anything, but I have something green. Sixpence in her shoe, I have no idea. So this is just, oops, sorry. So where's the pointer here? This one? Ah, yeah, okay. So this is just a sixpence penny from the Victorian age. Anyway, this was not supposed to go into this presentation, but I was inspired by Artem Cherkasov talk about how COVID changed our life as a scientific community. So I decided to have this. So what I'm showing here is the genome of the COVID virus. And what you see in the periphery is the structures which we have. And importantly, almost none of these structures was available before 2019. So the scientific community was faced with a challenge, and I think we responded to it quite nicely. And look what we have now after, I don't know, 4 or 5 years. So we have over 40 vaccines. We have 3 compounds to be treated as medication to people with mild COVID, and six compounds with medication for people who are suffering from COVID. So severe COVID. But obviously, this is not the end. And if you look today on the internet and you're trying to find what are the current challenges, then this is typically what you're going to see. So global health, water, energy, and so on and so forth. And I think that this conference until now mainly focused on this global. Can I get a better pointer? Somehow I'm unable to show what I have. Yeah, so now I need to work with 2 hands. Is it? Wait. Yeah, okay, fine. We'll manage. This conference until now mainly focused on the global health, but I'm trying to go and focus a little bit on energy. And you know the drill, right? We are using too much fossil-based fuels, which are responsible for global climate warming and the Earth environment. And we need to go to more green energy. The problem, though, is with green energy, if you're talking about solar cells, for example, or wind or sea waves or whatever, that it is not consistent. So we need 2 things. We need a way to harvest it on one hand, and then we need a way to store it. So this is a different issue. And I would say that Chemoinformatics can help in at least partially addressing these challenges. And this kind of connect to what Alex Stroker said at the first lecture of this conference. The paper is QCR without borders, so I changed it to Chemoinformatics without borders. And this is Alex Stroker's head on top of the Superman. So material informatics is part of Chemoinformatics or a sister field of Chemoinformatics. And as all informatic methods, it is used or it is fueled by data. We need data. And fortunately, we are beginning to have many data in the field. So these are just a few examples. So this is the NIST database. This is the inorganic chemical structural database with over 250,000 crystal structure. Over down here, the MapWeb, they have 160,000 structure. This is the growth of the Cambridge structural database over the years, updated to about 2 weeks ago. And right now we have over 1.2 million compounds with known crystal structures in the CSD, and the numbers are rapidly growing. The Genomic Material Project is producing many compounds with kind of the objective of accelerating compound development. And these were only experimental databases, but we have a huge number of computational databases. This is probably one of the most known one. This is their AFlowlib, which currently contain over 3 million compounds and over, I don't know, 733 million calculated compounds, all at high level ab initio method. The Nomad project has a lot of information in it. Again, high level computational chemistry calculations, the Q mode, and we can go on and on and on. But this is only probably the tip of the iceberg, because the size of the material space is huge, and to a certain extent, and in somewhat contrast to cheminformatics, is largely unexplored. And this kind of huge number of data is also reflected in the number of publications which mention material informatics. And this slide is a little bit outdated, but you see the trend. So this is the number of papers having material informatics in their title or in their abstract. But this is, again, just the tip of the iceberg. And why is this? So because we are in France, I had to put a citation from Molière. And this is an interesting discussion between the Master of Philosophy and Monsieur Jardin. And the idea is that for the first time, Monsieur Jardin understand that for all his life, he was actually talking in prose, and he was very happy to learn this information. And the message I have is that many people are doing material informatics without actually calling it by this name. So maybe we need to get our terminology right or not, but in any way, what I'm saying is that the number of actual papers dealing with material informatics is much, much larger than this one. And this is not my citation, this is John Nismay. So we're drawing in information, we're starving for knowledge. And I guess most of you have already seen graphs like this, which basically try to tell us that we can generate data and we can store data and we can retrieve data much, much faster than we can do anything useful with this data. And the idea is that cheminformatics, material informatics, all the informatic methodologies might help us to, I don't know, bridge this gap, solve this problem, or whatever else you want to call it. So let's take a quick look at what we need in order to do structure property prediction. And I have to make an apology. When preparing this lecture, I thought, who are actually my clients? And because this is a summer school, I understand that my clients are the students. Meaning that some of the things I'm going to say might be a little bit trivial from the more experienced researchers, but still, I hope you'll find some interesting stuff in at least part of it as well. So what is this that we need to know if we want to do a structured property relationship? So we need accurate experimental data, activities, and these would be our dependent variables. We need descriptors, and these are the independent variables. They could be structure drive, they could be process drive. I'm going to talk about it in a minute. And they could be measured, they could be calculated, anything goes. We need a mathematical model, which will be quantitative or qualitative, I know, KNN or support vector machine or very fascinating neural network. We need a way to validate the model, and today it is well accepted that models should be validated based on external tested. And it's probably would be good if the models are simple and interpretable. And this is well known, but this also gives me a nice framework to compare between classical chemoinformatics, more drug design chemoinformatics perhaps, and material informatics. So let's take it step by step. So the compounds. When we're doing kind of classical chemoinformatics, I know drug discovery-related chemoinformatics, the structures are typically very well defined. We know what the structures are, maybe building block, maybe large molecules, but we know what they are. And there are potential exceptions if we're working with polymers, and if we're working with mixtures, but even then, at least the constituent part are known. We know what the monomeric units are, and we know what to take into the mixture. And this is also true when we do combinatorial chemistry, and we've heard a lot about it. Now, in material informatics, in some cases, indeed, the compounds are very well defined, but in many cases, they are not. And this is particularly true when we're doing what is known as combinatorial material synthesis. Basically, pouring a lot of different material and looking what we come up with, and sometimes we even don't know what we have in our heads. So this generates a problem if you want to calculate descriptors, because you really don't know what to calculate. For example, we've been working on glass fragments. I don't have a clue on how to calculate anything on a glass fragment. The data. So if you think about it, chemoinformatics, the diversity of data comes mainly from the target. So kind of classical chemoinformatics is mainly concerned with pharmacokinetic and pharmacodynamic of ligands targeting different proteins. So most of the diversity comes from the targets and the ligand types. And we have data set of all sorts, medium, small, large, extra large. Material informatics is different because the number and diversity of endpoints is huge. Pretty much, again, everything goes, and I'm just giving here a few examples. Solubility and biological activity, and Young modulus and thermal conductivity, viscosity, melting point, solar cell. So the diversity is much larger. With the diversity comes a price. And the price is that some of the data sets are small to even tiny. And if you remember Professor Funazio lecture a few days ago, I think he mentioned a data set with 26 compounds. Now, in chemoinformatics, classical chemoinformatics, we wouldn't even look at something like this. But in material informatics, sometimes this is all that we have. The descriptors. So classical chemoinformatics, one-dimensional descriptor, two-dimensional descriptor, four-dimensional descriptor. I will talk about it today. I even saw five-dimensional descriptors and six-dimensional descriptor. I haven't got a clue what they are, but there are there. And we are using classical, we're using fingerprint, and almost never using QM calculation, especially because the data sets are so large. And we cannot calculate reliable QM descriptors of hundreds and thousands of compounds. Material informatics, again, if the compounds are well defined, we can use all of this. There is heavy reliance on QM descriptors, and we can also, and this is beginning to emerge, we can use experimental data as descriptors. And if you think about it, this is great, because the experimental procedure is something which we can easily modulate. You come up with a descriptor which tells you something about the hydrophobicity of the compound. It's not always completely clear how you have to change the compound to make it more hydrophobic or more hydrophilic. And hydrophobicity and hydrophilicity are easy examples. However, if you found out that that something good happens when you are heating the system for more time, that's very easy to do, right? Just heat the system for more time. So introducing kind of device information and experimental setup is important. And there is also a heavy reliance on measured descriptor. Again, if you have a glass fragment, you really don't have anything to calculate, but you can measure it. And as a result, there is heavy reliance on spectra of all sorts. And a spectrum is just a fingerprint of the molecule. And you can calculate and you can measure different spectra from almost everything. And you can use these spectra as fingerprints in any machine learning model. And people are doing it more and more and more. Algorithms. So people may disagree with me, but I really don't think that we need any different algorithm in material informatics than we need for chemoinformatics. And this is also true for forensic informatics and agriculture informatics and anything which ends up with informatics. The algorithms which we have are sufficient, they are good, you can always improve them, but these specific fields do not require new development, at least in this perspective. And so you have the unsupervised and the supervised method, which we all know and like. Validation. So again, chemoinformatics, classical chemoinformatics is well-founded. We all know about the OECD principle, and we are mostly following them. With material informatics, we have a problem because sometimes, because the data set are so small, we cannot do the kind of rigorous external set validation procedure, and we need to do I know, cross-validation and all other things, which are probably less accurate. And then there is the algorithm, so the workflow. And when people are talking about chemoinformatics, material informatics, they mostly focus on the core machine learning algorithm, be it SVM, neural network, decoder, encoder. But you need to remember that the core part is only, the core algorithm is just a part of a complete workflow. And no matter how good is this core part, if your general workflow is not good enough, you are not going to get a reliable model. And we have a nice devil here smiling at the workflow because he knows that the devil is always in the details. And it's not that you just need to execute each and every stage in a correct way. You also need to execute them in a correct order. And this is important. I'll give you just one example, which I often see. So a lot of time people are taking a data set, they are cleaning it, they're calculating descriptors, they're removing outlier, and only then they split it into training set and testing set. And this is wrong. Because the moment you do it, you are kind of contaminating your test set from information from your training set. The proper way to do it is to take your curated data set, split it at the beginning, and then do whatever you want on the training set and apply it to the test set. If you remove several descriptors based on the training set, remove the same descriptor from the test set. If you develop an outlier to remove compounds from the training set, use the same model to remove the outlier from the test set. Don't mix the two. And one more thing, if you are doing random split, which is okay, never do it once, because then it's a chance, either it works or it doesn't. Repeat your random split multiple times in order to get some, I don't know, statistical information. Okay, so this was kind of a little bit long introduction, but I think it was important. And now we're getting into green energy harvesting and storage. So for harvesting, we're going to talk about solar cell, and for storage, a little bit about batteries. And there is common thing in these to these two. And I'm only going to talk about solar cell and batteries, which have what I call a molecular trigger. What is a molecular trigger? A molecular trigger is a small molecule, well-defined, which without it, this entire device, be a solar cell or a battery, is simply not going to work. And why do I focus on molecular trigger? Because it makes my life easier. Because I have well-defined compounds, and then I can use physical descriptors and fingerprint and pharmacophores and whatever I want. So, and there is of course an implicit assumption here. And the implicit assumption is that the performances of the solar cell or the performance of the batteries are a function of some descriptor, which I can either calculate or measure or something. And if I can find this relationship, then I can perhaps understand what makes a solar cell or a battery a good solar cell or a battery. And if I understand, I can usually also design something new. So 60 seconds on solar cells. Conceptually, they're very simple. You have a system, you excite an electron to a higher level, and thereby you are leaving a hole behind. So you actually got a separation of charges. Electron is negative and the hole is positive. And then you run the hole and the electron and the hole through what is known as an NP junction. One of the part of the junction is able to conduct electrons efficiently. The other part is able to conduct holes or positive charge efficiently. You collect this charge separation via an external circuit, and voila, you have electricity. And there are many, many ways to characterize a solar cell, open circuit voltage, short circuit current, internal quantum efficiency. Most people are characterizing solar cell by using the power conversion efficiency, which is basically how efficient a solar cell is in taking sunlight and producing electricity. And there are equations over here to calculate it. So efficiency of solar cell have been growing over the years. They're still mostly, and what I'm showing here is the power conversion efficiency. They're still mostly based on silicon, but there are other alternatives. And the alternative I'm going to focus on are called dye-sensitized solar cell. They were invented by Michael Breitzel. just a fun fact, I looked at Google Scholar yesterday. He has an impact factor of 303, and the number of cited publication is almost 500,000. By now, it's probably 304 or 5. Sorry?
No, not impact.
No, sorry, yeah, H-index, so yeah, it's H-index, not impact factor. I apologize. Anyway, so these are dye-sensitized solar cell. How do they work? Basically, according to the principle which I just explained to you about. So there is a semiconductor. So there is a dye. This is the purple. And the dye is embedded in a semiconductor, which is typically titanium oxide. You excite the dye, and you are taking, so an electron jumps from the dye to the titanium oxide. You regenerate the dye, that is, you introduce back an electron into the dye using an electrolyte, which is typically based on iodine, but not always. And then you generate the electrolyte back. You generate the electrolyte in the counter electrode. And in this way, you are generating electricity. And the dye, what I previously called trigger, is a central part of this story because it is responsible for photon harvesting, the electron rejection, and to overall cell performance. In the past, most dyes were made of ruthenium compounds. So these were organometallic compounds with ruthenium. The problem is that ruthenium is a rather rare and expensive metal. The synthesis of ruthenium compounds are rather complex. And these compounds tend to have a low molar extinction coefficient, which is basically how strong a compound absorbs the light. And then people started to work on organic dyes, which are inexpensive, easy to synthesize. They have higher molecular extension coefficient. Only small problem, they're not that efficient. This changed to a certain degree when people have started working on organic dyes, which has this structure. So this is a donor, pi bridge, and acceptor architecture. So the donor gives the electron once it is being irradiated, and the acceptor accept it and then transfer to the titanium oxide. And this generated dyes with much better properties. So in 2018, this guy over here published a dye-sensitized solar cell database. Don't try to look on it on the internet. It was removed because this guy has problem maintaining it. But about 5 minutes before it was removed, we were able to just download it to our computers and use it. So in this respect, we were happy. It contains about 4,000 different entries, divided into like 10 different chemical scaffolds. We did some pre-processing. We removed the metal dyes, we removed the duplicates. We tried to generate a data set which is as uniform as possible. And our idea was, let's try to use this data set to do virtual screening. For virtual screening, we need a model. Which model should we use? We thought, well, let's try to use a pharmacophore model. Sounds like a nice idea, and people have not been using pharmacophores in material informatics. So we decided to focus on 4 families, which were rather large. These are the number of active compounds from the data set, from the database. And here overall on the right, we took compounds from the zinc as decoys, but we made sure that they contain exactly the same substructure as the active compound. Different decoration, of course, but the same scaffold at least. And we built a pharmacophore model. And after Thierry's talk, I really don't need to go into how one builds a pharmacophore model. We did it the classical way. We built many pharmacophore models. Some of them were based on specific scaffold. Some of them were based on the most active dyes. I'm showing here a few 3 pharmacophores which were based on active compound, and also 3 pharmacophores which are based on inactive compounds. The idea behind inactive compounds is to try to filter out false positives. Sometimes it works, sometimes it doesn't, but we gave it a try. We validated the pharmacophore model using ROC curves, and because we have so many, I'm not showing the actual number, but this is just a toy ROC curve. But again, nothing special here. And again, we did very, very simple, straightforward virtual screening campaign using the pharmacophore. We ended up selecting 35 compounds. The 10 highest scoring one based on some scoring function, which we devised, which basically give better score to compounds which match more and better pharmacophore models. And we also look in some hits, just looking at them and selecting them. Now, ideally, we should now evaluate them experimentally, but we didn't have a setup. So we decided we're going to evaluate them in an orthogonal way. Orthogonal way, meaning QM calculations. So we submitted all 3 certified compounds to reasonably high-level QM calculation, DFT, this is the functional, and also to time-dependent QM calculation in order to get the absorption spectrum. And here are the results. So in order for a compound to serve as a dye, it should have several characteristics. First of all, the LUMO, the energy of the LUMO should be higher than that of the titanium oxide. The energy of the HOMO should be lower than that of the electrolyte. So these are the 2 lines here. And the HOMO and the LUMO should sit on different parts of the dye. They should not interact among themselves. What I'm showing here on the right-hand side is an active compound, a real known active compound taken from the data set. And what I'm showing here are 2 compounds which came up from the screening. And as you see, they meet all the criteria, except one which we didn't like that much. If you look at the absorption spectrum over here, then the peak here is much broader and it is shifted a little bit to the right relative to these 2 compounds. So what did we do? I can go back, yeah. So we were working on these compounds and we just made 2 changes. We changed this moiety over here and this moiety over here to moieties which are more characteristic of dyes in solar cells. We got these 2 compounds, so the carboxyl group was changed to cyanoacrylic acid, and the succinamide was changed to this group. We still maintain good separation between the LUMO and the HOMO, both here and here. We meet the criteria with respect to the energy level, and we generated slightly broader absorption spectra shifted in the right direction. And we were happy about this. And this is where we stopped because, again, we didn't have the experimental setup to actually test it. So, and I forgot to say, this work was done by Hadar Binyamin, who was a master's student in my group. What about good old style machine learning? Why don't we try this one? So here's our first attempt. Non-optimized feed-forward neural network using Morgan fingerprints. And here are the results. Q square minus 0.77, really great. I mean, if it was plus 77, we would be happy. Minus 0.77 is bad. And why is it bad? Look at these vertical lines here. The vertical lines here represent, I'm giving you 2 examples of the same dye put in different devices, completely different setup, different electrolyte, different titanium oxide, different everything, just the same dye. Obviously, the cell performs in a different way. Now, what the neural network is trying to do is kind of average everything. So you see that the neural network generates the same prediction for all the dyes, for the same dye in different device configuration, because Morgan fingerprints do not know anything about device configuration. What is the solution? Introduce device configuration into the machine learning. So Paul was a PhD student in my group, took the entire data set and basically transformed all the experimental information into fingerprint. And there are a lot of technical issues involved in this, which I'm not going to go into it, but eventually he managed to do it. And he did it in 2 ways. First way, in a kind of actual numbers, and in the other way, he basically binned the device information into bins and used bins. And then we just tried to build a machine learning, again, feed-forward neural network, unoptimized, using just the device fingerprint. This is total crap, but this is actually not bad. Q square 0.55, using only device information, nothing about the dye, already tells you how much the device information is important in this. Now, the next step is obvious, right? Let's combine them together. So when we combine the device information with Morgan fingerprint and doing some optimization of the network, we actually get something which is not bad. all these vertical lines have vanished. Q square went up, Q square on the test set went up to 0.75, and this is actually pretty nice. The next thing we did about this, is doing some SHAP analysis. For those of you who are not familiar with the term, SHAP analysis basically looks at all the descriptor and tell us which are the most important one. And this is a model agnostic method. That is, you can apply it to any model you want, okay? So we apply it to the network, and these are the SHAP analysis. And you see that these two, which are marked in red, are actually device fingerprint, or these are information taken from the device. Some of them, these are the most influential, 10 most influential descriptors. Most of them are taken from the die, but at least 2 of them are taken from the device. Now, it's interesting because if you are now looking only at the low energy cells, nothing about the device. So it seems that the device information comes into play only when you go to higher and higher and higher PCE. For example, this is a medium case, medium range of PCE. You see one device information going in, and this is the high value only, and already see three device information. And the most influential descriptors actually comes from the device for high performing solar cells. Sorry. Okay, so far so good for solar cells, and now a few minutes about redox battery. So these are redox flow batteries. This is a special type of battery where you have 2 tanks over here, which contain, one of them contain the anolyte and one of them contain the catholyte. And these are small organic molecules, not always organic, small molecules embedded in a solvent. It can be water, it can be non-water, and we're going to work on non-water. And these are pumped into the electrode. So upon charging, the cycle goes in one direction, and upon discharge, it goes in another direction. So these two the compounds in these containers are pumped into the electrode. There is a membrane separating them, and you get electricity. Now, what's nice about them? Several things. First of all, the capacity. The capacity basically depends on how large the tanks are. You want a large capacity, generate large tanks. The compounds are reasonably easy to recycle, and this battery produces rapid response. But there are challenges. These batteries have lower density with respect to other like ion lithium batteries. Sometimes cross-contamination occurs here at the interface between the 2 electrodes. There is separating membranes here, but it doesn't always work perfectly. And all this device, the electrode and the separating membrane, should be very durable. So there is a lot of research going on with this type of redox flow batteries. State of the art is vanadium, but vanadium is a rare metal. It's expensive, it's toxic, and nobody likes to work with it. And as a result, again, new things are required. One more thing, when working with this type of redox flow battery, it's like in drug design, right? You need to balance several properties. So in this case, you need to balance efficiency with high voltage and long lifetime and high capacity. And we're only going to focus on this high voltage, at this stage, only on this high voltage. So we came across an interesting data set. And it was so interesting that we immediately got in contact with the publisher, and from now on, and we're working in collaboration with them now. So this data set is called the D3 Tails database, and it is intended to contain a lot of experimental and computational information on this redox battery. And the NA means non-aqueous. So non-aqueous redox flow batteries. Initially, the idea is to include here redox potential, solubility, sensitability, and so on and so forth. Right now, the database, the scheme of the database is ready, but it is mostly populated with quantum chemical calculation, high-level quantum chemical calculation of oxidation potential. The way this is done is the authors took the zinc database and the Cambridge structural database. They filter it until they got about 32,000 compounds. They employed high-level QM calculation, and they populated the database with oxidation potential. I'll show you in a minute how they did it. Why this database? Because it's new, because it focuses on non-aqueous system, which is interesting because, again, this is new. It contains QM calculations. So to the extent that the QM calculations are accurate with respect to experiment, trying to reproduce them makes our life a little bit easier. We don't need to worry that much about data curation. And also it accepts a submission from the community, which means it's going to grow and grow and grow and grow. So this is how one calculates oxidation potential. And this is not different than standard free energy perturbation cycles. Okay, so what you're trying to do actually is calculate this leg, in a solvent, and this is implicit solvent acetonitrile. So basically you want to calculate this process, the process by which a molecule loses an electron in solution. And because free energy is a state function, we can calculate it as the summation over the other three legs. And we can use the Nernst equation and get the oxidation potential. This is standard stuff. Nothing new about it. Is it good? Is it bad? So this is benchmarking against experimental data of standard redox compounds. And this is actually not bad. And this is some preliminary work they did on non-aqueous redox flow batteries. The correlation is not as good as in the aqueous redox flow battery, but it is still acceptable, at least in terms of trend. So these are pure compounds. This is the calculated oxidation potential. This is the experimental one. Again, correlation is not perfect, but the trends are there. And this is what we had. So this is what we were working with. So this is the work of Anna, who is sitting here in the audience and asked me to embarrass her. And I promised that I will, but I won't. So Anna started working on it. And she tried many things. SVM and RF and CAN, and with this descriptor and the other descriptor and this and the other, nothing worked. Absolutely nothing worked. And absolutely nothing continued not to work. So at this point, say, okay, fine. Maybe oxidation potential are too difficult. Let's try to calculate instead the adiabatic ionization potential. Now, what is the adiabatic ionization potential? This is the energy between this well and this well. This is the vertical ionization potential. That is, we do not allow the ion to optimize. And this is the adiabatic where we allow the ion to optimize. And this database had information about this. So Anna repeated all the calculation, all the method, all the descriptor. Now just trying to look at the adiabatic ionization there. And again, it makes sense, right? Oxidation is a process of losing an electron. So let's try if we can simulate a process of losing an electron. And actually, we got nice result. See, we're happy. This one and this combination over here, which is also nice. And then we did what we call one experiment too many. And this is something we should have done at the beginning. Look for a correlation between the adiabatic ionization energy and the oxidation potential. Zero, nothing. So the fact that we are able to simulate the adiabatic ionization potential doesn't tell us that we were able to simulate oxidation potential. So we were very sad again. And then we said, okay, maybe we're asking for too much. I told you before that this database was populated by data from two sources, Cambridge Structural Database and Zinc. So we said, okay, let's focus on the CSD data. Why? Because we have structures. Now, whether the structures are relevant or not, we really don't know. And this is maybe an important take-home message, right? Whenever you're looking at 3D structures, and Pavel talked about it in plants, you always need to think, is this relevant to my problem? Is the conformation of the compound the same in solution or when it is absorbed, for example, on the titanium oxide layer or whatever, or in the battery? I don't know. But at least we had structures. So let's start to work with them. And also, this is the entire database. And if you look, the CSV compounds kind of cluster a little bit, in a very good day, we can say that they cluster a bit, at least they are not that spread over the entire data set. This is, by the way, the oxidation potential, the histogram, and this is the molecular weight. We said, let's try to do this. So KNN, RF, okay, we're getting better. I'm showing here Q-score result on the test set, nothing on the training set. SVM, okay, we're beginning to be happy, reasonably happy, okay? And note also that there are several outliers. Now, I don't think that it is totally fair to just remove outliers because you are unable to model them. But in this case, if we remove 2 or 3 compounds and we get a boost in Q-score, I would say, okay, fine. We report it and let the community decide whether this is worth anything. So this is actually not bad. But then we said, okay, let's try to go to more sophisticated algorithm, graph convolutional network. And this is a succession of attempts, each time taking the neural network and adding some more information to the nodes. So in convolutional neural network, you can add information to the nodes. So we begin by adding just the atom type and aromaticity, hybridization, formal charge, chirality, electronegativity. It seems that you are reaching a plateau of about 0.51, 0.52. So adding more and more and more information at one point doesn't help anymore. And what I know, surprising, not surprising, it didn't outperform SVM. Happens. So these are the results we have until now. This is only for the CSV compounds. This is the best SVM we have. And if we remove like 2 compounds, we get to 0.65, not bad. This is the best graph convolution network which we have. This is kind of half optimized, not fully optimized yet. So we have to work on it a little bit. 0.58, and this is the RF, 0.55. This is where we are standing now. So we said, fine, we're staying. Let's see though if we can expand it a little bit. So how to expand? So we devised a very simple algorithm, which basically tells us the following. Let's try to find non-CSD compounds, which are very similar to as many CSD compounds as possible. Include them and see what we get. So our initial training set of the CSD compounds alone was about 2,000 compounds and about 1,000 compounds for the test set. After expansion, we pretty much doubled it. And these are the results. So in a way, we are back to square one. We are able to get reasonable model for CSD compounds. The moment we're trying to expand, doesn't work. So where to go from now? Our own feeling right now is that doing more sophisticated neural network probably not going to help. What might help is using 3D descriptors. Until now, we use mainly 2D descriptors, and 3D descriptors might do the trick. We still need to optimize some people parameters. If this wouldn't work, I'm almost done. If this wouldn't work, then cluster-specific models may work. The CSV by itself works. If we cluster the space into cluster, maybe we can get cluster-specific model. But basically, we're a little bit stuck here. So any ideas would be more than welcome. So to conclude, so this is my feeble experience in trying to convince AI to generate take-home messages. I tried it 3 times, and this is the 3 pictures it gave me. So take-home messaging, I think that Chemoinformatics can and should be used to at least help address current global challenges. I think that device information is critical, not just in solar cells or in batteries, everywhere. When you have device information, use it as part of your machine learning. Does anyone know, if you first don't succeed, Mr. Wayne, try again, Mr. Key. Does anyone know where this is coming from? No? Diamonds Are Forever from James Bond, one of the old movies. But this is a good method, right? It's never going to, you're never going to succeed the first time. If you are, consider yourself extremely lucky. It doesn't work, try again. Eventually, it will work. Collaboration with experimentalists is indispensable, really. We are doing this work on the solar cell, we're done experimentalists. This work on the batteries done in collaboration with experimentalists. Most important, have fun doing whatever you are doing. Thank you very much.
Great. One short question. I think the most popular question to be asked now is what is available for lunch?
And thank you very much for the interesting talk. I'm a little bit curious about the descriptors. I mean, are you including some sort of descriptors appropriate for describing the change of electronic states, because this kind of stuff is quite related to the oxidation reaction. They are purely electronics. That's why I'm wondering what kind of descriptors are prepared for that.
So we tried several. We tried fingerprint, we tried RDKit, we tried AlphaDeck. And we also tried to include some of the information which was available in the database as descriptors. The problem with this looking forward is that we cannot use this to do virtual screening because this would require for us to do QM calculation of the entire database. But what we're trying to do now is include some 3D information, which would perhaps be easier to calculate. But you're absolutely right. We are probably not using the optimal descriptors in this project.
Maybe you should better include descriptors representing the polarity of the molecules or charge distribution related quantities that might help you.
We will try. We did try to introduce electronegativity and it didn't help. But again, I agree we didn't do the best work here.
Thank you. Yes, so that's it, folks. Closing words.